which is kind of annoying. So, okay, with floats, if you want to take input with scanf, okay, scanf, so let me comment this so that it doesn't actually. Scanf, you use %f if it's a 32-bit float and %lf if it's a 64-bit double. But you use printf can only print 64-bit doubles. So if you have a 32-bit float that you want to print, you have to first f convert it up to a 64-bit and then print it. I don't know why the heck that is, okay? But that's just the way it is. So suck it up, buttercup. Okay. All right. So that was one kind of mildly annoying detail I forgot to point out last time. I think that was the only major issue to point out. Yeah. Okay. All right. So yeah, it's annoying, and I guess to be consistent, you could always just use LF, but because you're up converting things to that anyway, it doesn't really matter. Yeah, again, there's probably a reason why this is the case, and I just don't know what the reason is. That whatever the implementation of the C standard library is that's on the 64-bit ARM, it's just the way it is. So whatever. I guess two other things. Sorry, now that I think about it, is for the floats assignment, for the Magic version, you need to do 1 Newton iteration too, not just the magic trick, okay? And in doing so, you'll see a little bit more of, how floating point arithmetic works. For the built-in version, you can either do fdiv plus f square root, right? F square root would get you the square root, and then fdiv would do 1 over it, right? Or, well, if you put 1 in the right register. That was my intent here. But you can also, if you want, you can use the built-in estimation function, which is FRSQRTE, okay? So that will give you an estimation for 1 over the square root without having to do a division. And I think what you'll notice if you do that one is that its initial estimation is better than the magic trick's initial estimation, okay? And hence, when you do, okay, and the FRSQRTS, the syntax, you have to be very careful with that and basically look it up in the manual because it's not exactly the way you would think it would go. That does, in a single instruction, if you do the syntax correctly, will do the Newton iteration for this particular problem, okay? But like I said, you've got to look up you've got to dig into the manual. So do either one of them or both if you really want to have some fun. Yeah, okay, so makes sense? Yeah, okay, good. All right, so next topic is, let's go back to, I had my fun and exciting, I think it was floating point, or maybe it was the other one. Let me just double check that I've got the right one. Oops. No, it was the other one. Okay. Okay, so we did all that stuff. Okay, so this is what I wanted to start talking about today, which was SIMD, single instruction, multiple data. So let's suppose, yeah, question? Maybe. I'm gonna have to shut the whole thing down to, yeah, so no. Look at that screen. Um, okay, so single instruction, multiple data. And what the point of this is it allows you to um, accelerate a lot of the kind of math that you would need to do in linear algebra. Now, if you've never taken linear algebra, if you think back to, I mean, probably what, algebra 2 in high school, did you learn a little bit about matrices, right? And the kind of arithmetic that you have to do to multiply them or whatever, right? There's a lot of things where you have to multiply the stuff pairwise and then add up a bunch of crap, okay? And that's something that where you're doing the same sort of operations on lots of different objects. And if you could parallelize that, then you could do stuff obviously a lot faster than doing it sequentially. But like, so let me maybe back up a second to say, there's a lot of stuff that you could parallelize. The question is it worth building circuitry to do it and speed it up? Is it something you do often enough for it to be worth having extra complicated circuitry to speed up that kind of operation? Okay. And uh, in the case of things like the reciprocal square root or this single instruction multiple data stuff, the answer is yes, right? The inverse square root gets used all the time in computer graphics because if you've got a vector and you need to compute a vector that has the same direction but only has length 1, well, then you have to divide it by the vector by its own length, and the length you get by doing a square root computation, right? Think like in, if you do like Pythagoras' theorem kind of thing, right? That's a square root. Well, if you need to divide by that square root, you're doing an inverse square root, so, or reciprocal square root, right? So you need to be able to do that sort of thing quickly because it's something that gets used so often in computer graphics that it's worth speeding up. The linear algebraic kind of stuff, or things that can be sort of translated into that language, are sort of similar, okay? And so the SIMD unit um, in the arm floating point allows us to speed up uh, certain kinds of operations that are sort of linear algebra looking, okay? Okay, so just to review, the SIMD or the floating point unit really has 128-bit registers, okay? Um, and they're called V0 through V31. Um, and you can subdivide these into a couple of ways. Now, the way we've used them is basically the D0 or the S, D something or S something, which would be the lower 64 bits or the lowest 32 bits respectively, okay? And we just dealt with it sort of one at a time. But if we want to pack these things together, we can pack, well, at 128 bits, how much room is there? Well, there's room for 2 doubles, 4 singles, 8 halves, or 16 bytes, okay? And the graphic, which I think I had in the other one here, no, maybe it was in this one. I had a picture. Here it is. Yeah, that's what I wanted. Okay, so there's sort of the picture as to how this thing is subdivided, right? So look at what we've got. Vn would be the whole bloody thing, the whole 128-bit chunk, okay? And then if we carve it into 2 doubles, we've got Vn dot 2d brackets either 0 or 1, meaning the low chunk or the high chunk, okay? And then if we carve it into 4 singles, then we've got v whatever dot 4s, 4 singles, and then which one are we talking about? Well, either 0, 1, 2, or 3, right? Sort of from lowest to highest significance positions. And those are the only 2 carvings that I think we'll particularly use. But you could, if you wanted, carve it up into 8 words, which are 8 16 bit things, or 16 bytes if you wanted. And if the structure of your problem is such that you only needed to use like 4 words, then you can carve it up into 4, half precisions instead of having to carve it up into 8 half precisions. The bit width is obviously the exact same, but it's just like, if you don't need 8, why bother with talking about 8 of them, right? So anyway, the half precision thing, you might think, well, why is that useful, right? So if we've done 32-bit floats, you can do 16-bit half precision floats. You just have to change some of the numbers a little bit, but it's the same idea. In machine learning, 16-bit half precision is sort of good enough. And it's obviously, because it's half as many bits, you can either cram more data into the same space or possibly process with it faster. So if it's good enough, then why not just use 16-bit halves? For something like computer graphics or serious scientific computing, for the most part, you want to do 32 or maybe 64-bit. And if you're really like, if you're, I don't know, like running the Large Hadron Collider or trying to do a numerical simulation of the formation of the solar system, then you'd probably need like 128-bit precision. But that's kind of those are specialized kind of purposes. All right, so anyway, so we can carve these things up, and what we're going to do is we'll do sort of a single precision example, and then you guys will do a double precision version. And we'll look at just a quick starter example of how to do a simple sort of linear algebra computation. And then we'll look at some code I wrote to do a trig function approximation, okay? Because there's no hardware trig function on these machines. There sort of can't be for technical reasons. Anyway, so we're in our example going to use the third line from the bottom here, vn.4s. We're going to carve up our thing into 4 single precision floats and then deal with them accordingly, okay? Okay, and the v stands here for vector, just FYI. Okay, so if I take 2 vectors here, and just for sake of demonstration, I've picked 1, 2, 3, 4 and 4, 3, 2, 1. Okay, so in linear algebra, one of the kind of operations you have to do a lot of is the dot product, where you basically take each corresponding entry, you multiply them, and then you add all of those products together. So in this case, we would take the 1 and the 4, the 2 and the 3 and the 2, and the 4 and the 1, and we would multiply them each pairwise, and then add up and get whatever we get. And in this case, we happen to get 30, okay? I just picked easy arithmetic for the sake of the demo. Okay, so is that all right? Yeah? Okay, and then the other thing, of course, I need is that I need to load in my data, right? And in this case, because the numbers are simple, I could F-move them, but I'm deliberately not, to sort of illustrate one other thing, which is how I can have sort of like a table of things. So vec1 is going to be this vector that really is comprised of 4 words, okay, 32-bit objects. And I just, encoded 1, 2, 3, and 4 using float toy, but using the floating point encoding, so we don't have to think about that. That happens to be the encoding for all 4 of those numbers, okay, as floats, not as integers. And then, of course, my other vector will just be the same thing, but obviously in opposite order, because I just picked the same numbers. Okay, so does that make sense? So I'll need to put obviously those in my data section, okay? And then vec2 is the same thing, but just in opposite order, okay? So let's go into here and let me make a new document. And okay, so we need data, we need text, we need global main, we need main, we need the usual store and push and pop the link and frame pointers. All right, so all this is the same drill as pretty much every time we've programmed this semester. Okay, so nothing special there. Okay, and then, oops, damn it. Let me go ahead and save it real quick. Let's see, documents, no, not downloads, documents. Examples, make a new folder for SIMD, create, we'll call this SIMD1. Okay, so that's all as before, okay, and then I need to just, in this case, I'll just copy and paste all of this, right, up into our data section, and then get the tabbing right so that it, you know, because I'm majorly anal. Okay, and then vec2 is going to be the same thing, but just in reverse order. So I'll do this one first, this one second, this one third, and this one fourth. Okay, so nothing particularly special there. I just picked some random numbers for the sake of demonstration. Okay, so now that I've got that, I got the two numbers defined. I need to load them into the appropriate registers, okay? And the way that I do this is, so new instruction. Well, the first two instructions there are kind of the usual thing, right? LDR x0 and x1 with the addresses of this vector1 and vector2 objects. So that's a pointer, basically. And then the new instruction is this LD1 instruction. And what I'm basically telling it is, okay, I want you to go out to x0 in memory, and you're going to find 4 single precision floats there, load them in, and load them into, just for the sake of demonstration, I picked registers 16 and 17, carved up into 4 singles, and you need the curly braces, okay? Just the way they designed it. Okay, so all that's going to do, right, is go out into memory, grab those things, shove them in the register, and that's that. Okay, make sense? Yeah? Okay, so what was it? LDR x0 with the address of vec1, LDR x1 with the address of vec2, and then LD1 v16.4s with stuff from x0, pointed to by x0, and LD1 v17.4s with x1. Okay, so all that's going to do then is, if we were to look at the v16 and 17 registers after we executed those things, we would see 1, 2, 3, 4, or 4, 3, 2, 1, depending on which one we looked at, right? Because I just did one of them backwards order of the other. Okay. 4 singles, right? Because we're loading in here 4 32-bit numbers, and S stands for single precision. And then, of course, there's 4 of them because Well, that's how many I'm packing in. No, because each of the vector registers is only how wide? 128 bits. So you can fit 4 singles at most into a single vector register. And yeah. Okay, so got that. And then now we want to do some computation with it. So once we've got the data loaded in, we want to actually do something. Okay, and the way that we can do something is, oops. Okay, I can multiply corresponding entries. Okay, so fmul, well, that's going to do floating point multiplication, right? But by giving it a vector registers as opposed to just S or D registers, what it's going to do is it's going to take each of the corresponding entries from the 2 source registers and multiply them together and store their products in the corresponding spots in V18, okay? So if, for example, let's see, what do we have? In V16, we had 1, 2, 3, 4, right, like that. And in V17, we had 4, 3, 2, 1, right? If after I do that fmul operation, sorry, after I do the fmul operation, what am I going to have? 1 times 4 is 4. 2 times 3 is 6. 6, 4. Okay, so that's what would appear in V18. Or I'm sorry. Yeah, sorry, V18, reading the wrong line. Was those pairwise products, okay? And this is what's the beauty about the vector stuff, right? Is it did all 4 of those multiplications in a single operation. Whereas if we had put this stuff in S or D registers, we would have had to do 4 fmuls to do this. Yeah. That there are 4 singles. So that's what tells it that, hey, this thing is carved up into 4 single precision things, and so you've got 4 multiplications to do, and they're single precision objects. No, you can't do 5S because, and that was Mr. Steezy's question, right? Because how wide are the vector registers? 128 bit. Well, that you can only fit 4 32-bit things into that, okay? So what else could that be? Well, it could be, oops, any of those, okay? Oops, damn it. So it could be, let me stay where I can see, and it could be 2D, 4S, 8W, 16B, 2S, 4H, 8B, and then just regular D, S, H, and B, right? So those are the only things that you can do. And you'll sort of notice here that there's an extreme preference for multiples of 2, or really powers of 2. Gee, I wonder why that is. It's almost like everything's in binary or something, right? The what now? B? Byte. Yeah. Yeah, so it'd be an 8-bit thing. Yeah, so B for byte. And this is a little funny, and of course they had to do this, but, or, I don't know why they had to do this actually, but 8W versus 4H, the widths of the things are the same, but they used an H here and a W there. I don't know why they didn't do 8H and 4H, but then there's 8B. Yeah, I don't know why they did that. use H in one place and W in another. Yeah, exactly. Let's get ARM on the phone. If there's an ARM engineer out there on Twitch listening, then we need an answer for this, like stat. Okay. But you know, some of this is just Tufsky Shitsky, right? As they say in Poland. You just have to, you know, you didn't get to define the assembly language, so you just have to deal with it as it is. Sorry. You never heard that one? Yeah. Okay. So anyway, so yeah, so that's how we carve this thing up. So we've loaded the stuff in. Fmol is going to do the multiplication like we sketched up there on the board, right? And then what do I need to do? I need to add the corresponding pairs, okay? And this is a little bit annoying because what it's going to do is, okay, so what did I use for this one? V19. Okay. So V19, if I add these things pairwise, here's how it's going to go. And these are all .4s because of the way I'm doing it in my example. And I really should have brought my colored chalk, but those two are going to get added up and put into the bottom box. The next two are going to get added up and put into the second box. Weren't we supposed to get 30 from this computation? Okay, 20. Yeah, I just can't add. My bad. Because, yeah, I think 10 plus 10 the last time I checked was in fact 20. So, yeah, okay. Okay, so when I do this, the first part of step 4, F add P is floating point addition pairwise, okay? And so what it's going to do is it's going to take the 4 and the 6 that are in the first and second spot, add those together and put their result in the first spot. It's going to take the other 4 and the 6 from the third and the fourth spot, add them together and put that answer in the second spot. Okay? All right, so is that okay? Yeah? All right, now we obviously need the number 20 out of this. So the last thing we need to do is add the 10 and the 10. And the way that we're going to do that is look at the bottom instruction, okay? V19.2s. Well, we're only working with the lower two parts of it, so that's why it's 2s and not 4s, okay? And then if we add two singles together to get a single, where do we put single numbers? Single floating point singles. In an S register, okay? So that's why that last one there is V19.2s is where I'm pulling the data from, but the answer goes into an S register, and I just picked S0 here because I wanted to print it later. Yeah, okay, Connor?
So like V19.4s, whatever, like are there zeros in the other two symbols?
Yeah, basically. And we're just sort of ignoring that data.
And so what would happen if you just tried to put it directly into the S register?
It wouldn't work. Well, the assembler would throw an error because it would say, okay, you can't put two singles into a single, right? And if you put a D there, it would also complain because it would be saying, hey, you're trying to give me two singles to put into a double register. Yeah, the number of bits adds up, but you can't do that, bro. Okay, so the assembler would catch that and yell at you. Okay. Um, okay. So now we just need to program that in. Okay. So all right. So let's do that. So what did we say we needed to do? We did F mol of V v18.4s was our source, and we were doing v16.4s and v17.4s as our sources. Right, good there? All right, so that did the pairwise producting, and then we need to do 2 additions worth, sort of cascading, if you will. Okay, and so it was f add p, and we were going to go into v19.2, was it 4s or 2s? 4s. Yeah, and this is one thing that's a little bit annoying, right? Okay, so v18 pairwise added goes into v19, and then we did f add p, s0 with v18.2s, okay, or 19, sorry. Now, I don't like the way that they did this because you see how we've got 4s and then 2s? It would have made a lot more sense to me if they were both 2s in this case, because that's how many ones that we put together, but this is just the way it is. Sorry, right? I didn't define the language. So, yeah. Now, for doing this in double precision, it actually makes some things easier, because if you're only carving everything up into 2 big chunks, you only ever have to do 1 add pair, right? Because there's only 2 things ever to add. But what you do have to do is a lot more multiplications, because you can only store half as much data in each vector register, because each piece of data is bigger. Okay, we'll look at that later. S0, because the result of adding the 10 and the 10 is a single number, right? And where do single 32-bit floats go? They go in S registers, and I just chose S0 because I want to print it in a second. Yeah. We have to put it in S. And what's the difference between S0 and X0? X0 is what? Evan? Oh, okay. X0 is an integer register. S0 is a floating point register. And all of these numbers we're treating as floats, not as ints. You can only do this with floats. Oh, no, because it's a 32-bit integer, not a 60 or a number, not a 64-bit number. Okay, but you can do that with integer registers, but not with floating point, because like floating point, right, has to store the mantissa, the exponent, and the sign bit in appropriate spots. You can't just magically do that. Now that's different than integers because of the way integer encoding works, right? Yeah, so no, you cannot, there shall be no mixing of kinds. Okay, good? Yes, Evan. Did I? Oh yeah, I think so. Okay. Actually, I'm not sure if that's correct. We'll assemble it and we'll find out. Okay, now let me throw a format string out here for printing. Okay, and then the last thing I have to do, of course, is this, because I have to print it. Okay, so those 3 lines are just going to print it. So remember, what's the issue with printing floats? You only can print them as 64-bit, not 32-bit, so I have to convert a 32-bit thing up to a 64-bit thing. Farden, why are you look like you're about to have an aneurysm? Oh, yeah. Well, you know, you could move 1 row up and then right? Or one row back or one row forward, right? Yeah. So anyway, or you can tell Farden to stop being Farden. So yeah. Okay, so yeah, those last three lines there are just for the sake of printing it to make sure that we get, you know, data that looks reasonable. All right, so let's test it out and make sure that I haven't screwed anything up. And then we'll go through GDB to really see it in action. Okay, so good? Yeah. Pairwise multiplication, pairwise addition, pairwise addition. I've still got to add the 10 and the 10. So this last operation here adds the 10 and the 10. No, because there is no format string to pass printf a vector register. That doesn't make sense. Yeah, yeah. Or you have to give printf one number at a time, right? Okay, so let's do it. Oops. Damn it, where did I put all this stuff? All right, so SIMD. All right, so let's do as.g, simd1.asm, output simd1.o, and gcc. Oh, yeah, the ampersands to string multiple commands together? Yeah. Really? Oh, okay. Well, you can do that, right? Yeah. All right, so we got 20, right? That's, of course, what we were expecting to get. And it's printed, obviously, 6 decimal places there because that's the default for printing floating point numbers, is to print 6 after the decimal point and then however many to the left of the decimal point are needed. You can, and so in the format string, you could do, for example, let me come back up here to there to the F. I could do something like 5.10, and that will do 5 before, 10 after. Now, in this case, what it did with the 5 before is, well, there's really only 2 before, so it didn't print leading zeros. I think there is actually a way you can force it to do that, but we don't really need to. So anyway, so yeah, you can control the number of decimal points printed, but for the sake of demonstration, the default 6 is usually fine. Yeah. Okay, and now let's look at this in GDB, just so we can kind of see each of the stub operations happening. All right, so okay, so I'm loading x0 and x1 with pointers, right? So x0 has one memory address in it, and x1 has another memory address in it. And if you look at these, right, 3e and 4e, that makes sense, right? The assembler is going to put these things sort of in order in memory. And how many bytes are there between 3e and 4e? 16 bytes. Well, that's exactly 4 times 32 bits, right? 16 bytes is 128 bits, and 4 times 32 is 128 bits. That makes sense, right? Okay, so then if we load those two things in, I'm about to do the multiplication. So if I look at V16, okay, this is a little, actually, I think you can do this. Nope, you can't do that, which is annoying. Okay, so yeah, I don't really like the way it formats this. If I look and say, hey, what's in V16? it carves it up into all the different possible ways. And then, of course, we've got to look at the ones that we actually care about. And the ones that we actually care about, I guess, would be the second line, that sort of U in the middle there, right, is the version that's sort of helpful because we can see all four numbers individually. 3F80 blah 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 is 1. 4 and then all zeros is 2. 404 blah 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 is not found. And 408 blah 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 is 4. Oh, come on, I don't get any laughter out of that one. 404 not found. Huh? Like a 404 error, website not found. Yeah, sorry. Okay, but anyway, all four numbers are there, right? We can see them. Yeah. And then the same thing would be true for V17, except, of course, they're in the reverse order because I just picked that for sake of demonstration. Okay, and so if we step and we do the pairwise multiplication, let's look at V18, right? So what do we see in V18? We see this here, okay? And 4080, we already knew was the encoding for 4 because we've seen it already, right? And then what are the two dudes in the middle? Those are the encodings for 6. Okay, and of course we could check that with the float toy or sit down and decode it by hand. All right, so there we go. We did our pairwise multiplication, and everybody's sitting where I said it would. Okay, good, Gucci. Okay, all right. So now, what's the next operation? The first pairwise addition, right? Where I take 4 things and add them pairwise to produce 2 things. So that's one operation. And then I'll take 2 things and add them pairwise to produce 1 thing. Okay. All right. So the next instruction is 4 things became 2 things, and they're in V19. Okay. And so if I look at V19, what I've got is there are my 2 copies of 10. Now, to Connor's question, what went into the other 2 things? Not actually zeros, but just another copy of those 10s, which we don't care about. So, I mean, we're ignoring them anyway. So it didn't matter what got put there.
Is it adding everything in there?
Well, it added pairwise, right? So it did 4 and 6 to get this 10, this 4 and 6 to get that 10. And the fact that it's just sort of put a second copy of everything in the other 2 is...
The last operation is adding 10 and 10, so why wouldn't that be 40?
Oh, because I haven't executed that yet. Oh, okay, sorry. I haven't executed that next operation yet, but the next operation only adds the 2 that I've highlighted because the next one, so here's the instruction, right? V19.2s, not .4s, right? Okay, does that make sense? Yeah. All right, so those 2 things that I've got highlighted are the 10 and the 10, and then we've got some other copies of 10, but we don't care, right? They're garbage as far as we're concerned. Yeah. Add up the lowest 2, yes. Like the first and the third, for example? Yeah, yes, but with a different syntax. Okay. So if you put, V19.4s and then a bracket, right? So let me just write this. If you want to get a specific entry out, so this one is V16.4s bracket 0. This is damn it, v16.4s bracket 1, and so on, right? So if you want to get a specific entry, you can do that, okay? And the bracket thing, right? Think about this like in C. It almost looks like the way you would do an array or a string, right? Well, there's a good reason for that. Yeah, Connor.
So I have a question, like when you're doing the second half pair
Mm-hmm.
into two symbols, or you're adding this pair of two symbols, wouldn't you have one symbols being 21, but also the second symbol being 21?
No, because look at the destination. It's a single S register, right? So what I am not doing, all right, so what was it you got? I had tens, right? So there was this data, right? If I did two pairs of 20s, then the instruction would have been f add p comma, or sorry, f add p v something dot 4s comma v something dot 4s comma v something dot 4s, right? So if I wanted to add them, the two pairs and crunch them down, I could, but then the syntax would look, well, exactly like this when we did it for the fours and the sixes, right? But that's not what I want to do here. I want to take the first two, add them together to get a 20, and I don't care about the other ones, right? And so that's why I put 2s here, because I only care about the lower two. And that's why I put a single s here, because that's a single 32-bit float result, and it doesn't need to be vectorized because there's no other crap to go with it. Okay. And the only reason I put it into S0 here is because, well, I was thinking, one or two moves ahead that, hey, I need to print it and it's got to be an S0 anyway, so might as well just put it there now, right? Okay, so is that all right? All right, so we're about to execute that operation, and if I look at, sorry, S0, then of course, what do I see? I see the encoding for 20, okay, as a 32-bit float, right? And then the rest of the program just prints it, right? Okay, so does that kind of make sense? Yeah, I know it's kind of a lot to keep up with, but it'll sink in. Okay, all right, so let me quit this program. Okay, so good. All right, so the next thing I wanted to do is, let's see, make sure I've got that. Oh, and then we just did the printing. Okay, and demo time. Okay, so Gucci, right? All right, so that was a contrived example, well, semi-contrived, right? This is the kind of thing you would do in linear algebra all the time, but let's do this, something actually useful with it. All right, and so for that, let me go to Canvas, because that's where I've posted it. I probably have a copy on here, but I'll just show you where it is on Canvas. If you look at the Pyatt book, he has some sample code for doing sine computation, like sine is in the trig function. And I rewrote his sample code into what I think is a little bit more readable form. And in doing so, also changed the order a little bit to make it, like I said, I think a little bit more readable. Okay, and my example, it's in here in the files section. It's called sine of pi2x.asm. So let me download that and let's take a look at it. Oh, I already had a copy of it. Okay. Okay. All right, so two differences here. One, I'm going to do it in this one in 64-bit as opposed to 32-bit. Similar idea, okay? And then I happen to have a much bigger coefficient table. All right, now for those of you who have never done calculus, you haven't seen Taylor polynomials. Okay, so what a Taylor polynomial basically does is, so let me just take the graph of sine of x and sketch it on the board, right? So this part we should all know, right? So we've got 0, pi, 2 pi, pi halves, and 3 pi halves, and 1 and -1. Okay, great. And of course, it just repeats over and over and over again. So what I could do is, if I want to approximate the value of the function near to a certain point, and let me just pick a point kind of arbitrarily. So let me say pi over 4, just for sake of demonstration. And I compute the equation of the line that's tangent to it at that spot. Okay. Now, Arthur, you're not in calculus, right? You're in pre-calc. Yeah? Okay. Who else has not yet taken any calculus? Okay. You better be signing up for calculus next semester, bro. We should talk. Okay. You want to do the CS major, right? Yeah, well, then sign up for calculus next semester. Okay. Although you should be warned, because two things. The guy who's teaching it next semester is the most incompetent person in the entire department, and it's at 8 a.m. on Monday, Wednesday, Friday. I couldn't imagine who that might be. Yeah, who would be so cruel as to teach calculus at 8 in the morning? Yeah. Oh, and who would be so rude as to diss a colleague in his department and say that they're the worst professor on campus ever? Yeah. Yes, Dr. Gates is teaching calculus at 8 a.m. He's the worst. Yeah. So, yeah, and actually, in a just world, a perfectly just world, I would like resign and give my job to Dr. Gates, because I think he deserves it more than I do. I don't know. All right. Anyway, so tangent line, right? Think of like tangents from geometry, right? Same idea. How you find them is using some techniques from calculus, but if I just draw the picture, you're sort of convinced, okay, yeah, I can figure out what line touches at that one point and doesn't, cut through the curve near there. Well, if I want to approximate the value of the function, the squiggly, near to that point, I could just approximate, so if I wanted to do pi quarters plus 0.1, I could plug it into the equation for that line and get a pretty good estimate for what sine of pi fourths plus 0.1 is. Not going to be perfect, but it'll be pretty good, at least as an estimate. Okay. All right. So what about if I'm really clever, though, and instead of doing a line, I do like a cubic polynomial, right? So a cubic polynomial, depending on how you construct it, could look something like that, right? Well, this little chunk of it is kind of looking like that, right? It's not going to be perfect, but it's kind of close, yeah, right? And then I could say, well, what about if I do a fifth degree polynomial? What do fifth degree graphs kind of look like? Did I do one too many hump? No. Okay. Yeah. Sorry. I love my lovely calculus lump. Yeah. You guys know the song? My hump, my lovely lady lump. No? Yeah. Okay. Well, that kind of looks like sine with a few more of the squiggles, right? And if I kept this game going and started building higher and higher order polynomials, then I could approximate sine for, well, as much of a range of it as I want. Now, for government work, 0 to 2 pi is sort of enough, right? But that's sort of the idea. Okay. Now, the function that I'm going to deal with is not sine of x, but rather sine of pi over 2 times x, okay, is the particular function that I'm going to work with instead of just the OG sine. There's good reason for that. For one, what's the range like? Well, 0 is obviously 0, but then what's this point here, right? So what do I have to plug in to get, well, if I plug in, let's say, 1, then that gets me there, right? And if I plug in, well, yeah, it just changes the scaling a little bit, right? And the reason I picked sine of pi over 2x is because of a historical program that I want you guys to look at later. Okay, so what I have to do though is, and let me open up Desmos here for just sake of quick demonstration. Well, yeah, except so I don't have Mathematica on here because there's not an AArch64 version of Mathematica yet. And believe me, I've talked with the folks at Wolfram and been like, can has, right? Okay, so yeah. Okay, now I happen, because I'm a calculus teacher, happen to remember, right, the magic coefficients to make this work, okay? And so my red curve there is, of course, sine of x, and my blue curve is a 5th degree polynomial that between the first valley and the top peak, at least at this zoom level, you can't even tell the difference between the two functions. Okay, so this is a damn good approximation, and it's only 5th order. Okay, and I could keep this game going all day long, right? Now, the other thing is, you notice how that I have minus, and then I've got a coefficient of 1 over 3 factorial, and then the next coefficient is positive with 1 over 5 factorial, and you know what the factorial operator is, right? What's 3 factorial? 6, right? Because it's 3 times 2 times 1, okay? All right, so how do I know what those coefficients are? Well, because I know calculus. All right, now, if I want to do sine of pi over 2x, all of those coefficients change, right? Now, they change in a very predictable way that is not too hard to sit down and compute, but I had to recompute all of them, right? And then I had to encode them all as 64-bit doubles. That, I will have you know, took about 2 hours of my life that I will never get back. And you guys are very, very fortunate that there beeth the coefficients as 64-bit floats, all the way up through the x to the 15th term. Okay, you're welcome. Okay, pardon. Well, okay, the other thing is, so sine is an odd function, yes? And by odd, we mean it has origin symmetry, right? The odd functions only have the odd powers appearing in this series. And so I knew that the even powers all had coefficients of zeros, so why bother, right? I'm only going to add up the odd ones anyway. Why add up a bunch of zeros? Ain't nobody got time for that. Okay. Hmm? Yeah, well, and because I knew that the function I'm dealing with only was going to have odd powers. If I were doing this with cosine, for example, it would only be even powers. If I was dealing with some other function that was like a mix of sine and cosines, well, then I'm probably going to have odd and even powers, and I just have to keep track of it. Okay, but for the case of sine, I only need the odd ones. So because the even ones are all zero anyway. All right, so that happens to be the set of coefficients going all the way up to the x to the 15th term, which is going to give us a highly accurate approximation. Okay, now what I want to do though is, so let me go back to Desmos, right? Instead of computing sine of blah, I'm going to compute this polynomial of blah. Okay, now obviously it's not the polynomial exactly that I have it in Desmos. The coefficients are different because I'm not doing sine of x, but rather sine of pi over 2x. Okay, good. But anyway, there is this polynomial, okay, and this thing is called a Taylor polynomial after Brooke Taylor, a Scottish mathematician. And so all I'm going to do is, instead of computing sine, I'm going to compute this polynomial of that thing. Now, if the polynomial goes out to the x to the 15th term, I've got a crap load of stuff to compute. Well, if only we had something that was able to do a lot of similar looking computations kind of in parallel. Wouldn't that be great? We could even call it single instruction, multiple data. We can make millions. What do you guys think? SIMD, yeah, right? Okay, so here's how my little snippet of program works. Okay, the first thing that I'm going to compute, right, is I know that I'm going to need various powers of x. Okay, the number that comes in. Okay, and in this case, I've written this as a function that could be used by another program. So what is sitting in D0? Have I put anything there explicitly right now? No, but that would be the input that's coming into this function. Okay, whatever it is. So for sake of demonstration, let's just pick x equals 1, because what's sine of pi halves equal to? Just 1, right? So we should get 1 or very close to it out of this. Okay, so pretend that D0 is your number, okay? All right, and then I'm going to compute, I need x squared, x cubed, x to the 4th, and then I'm going to start building some basic vector pieces together, okay? And the way I chose to do this is sort of with some cascading powers there. And the, let's see, right, so I'm going to compute powers 1, 2, 3, and 4, okay? And then I'm going to start to pack these into a couple of vector registers, and this maybe answers, Cole, your question, or whoever asked it, how do you get a specific entry out? Well, like that. But in this case, I'm actually building the vector register from specific entries. Okay, so I'm sort of doing the opposite procedure. So I wanted to build the registers V4 and 5 by sort of copying data from the low part to the high part in both cases. And so now over there, if you look in my comments, I've sort of sketched out V4 has 2 copies of x to the 4th, and V5 has, in the high order spot, the x to the 1st, and in the low order spot, x to the 3rd. Okay, now you might think, why did I do it in that order? But what's going to happen if I do a pairwise multiply of those two guys? X to the 4th times x to the 1st is going to give me x to the 5th and 7th. And then if I multiply that again, I'll get 9 and 11. And if I multiply that again, I'll get 13 and 15. Right? So I was being smart here to try and organize it so that I would have pairs of powers of x in each vector register, kind of going up however many I needed, right? So then in V5, 6, 7, and 8, I've got x, x cubed, x to the 5th, x to the 7th, 9th, 11th, 13th, and 15th all together, right? And now I just need to multiply all of them by their appropriate coefficients and then add everything up. Okay, so this is why I think I like my code. I mean, I'm obviously a biased source here, but I like my code a little bit better than the one in the Pyatt book for this, because I think it's a little easier to see how I built it together. Okay. Okay, so then I need to load in all my coefficients. Okay, and this is where it gets a little bit fun, right? Because how many coefficients do I have that I need to work with? I've got 8 of them for x to the first up through x to the 15th, and of course I'm skipping the even ones. Okay, so there's a total of 8 of those. Okay, and I need to pack those guys into some registers. All right, now, I'm loading in X0 the address of this table of data, right, which I called C-tab Taylor 64, coefficient table Taylor polynomial 64 bits, okay? And now, what does the pound 16 do after, when it's there, after a comma? We've seen that before. We've seen it when we've done LDP, for example. What does it do? No, it's a post increment, okay? So what that's going to do is it's going to post increment the value that's in X0 by 16, okay? So if we think back to the way the coefficient table is arranged, if X0 is the starting address, that first instruction is going to load in those two things, right? And then X0 needs to point to where? The next two of them. Okay, well, where does the next one start? The next coefficient. It's 16 bytes further down from where we started, okay? So we've previously done this post-incrementing only ever with the stack pointer, right? When we did our LDP stuff. But we don't have to only post-increment the stack pointer. We could post-increment anything, right? And in this case, I'm post-incrementing my pointer that's sitting in X0 so that I'm moving sort of 2 entries down in my table every time I load in a previous 2. And I'm post-incrementing because I only want to increment after I've loaded stuff in, not before, okay? Pre-incrementing or pre-decrementing, you can do that, but here we want post, okay? All right, so those 4 instructions, or 5 if you count getting the pointer, okay, are going to get all of my coefficients into 4 of the vector registers, okay? So look at what I've got. I've got sort of a parallel structure. In 5, 6, 7, and 8, I've got the powers of x. In 16, 17, 18, and 19, I've got my coefficients, and I need to do pairwise multiplication because I need to do C1 times X1, C3 times X3, C5 times X5, and so on. Okay, so that's the next thing. And then I need to add it all up. Okay, so is that okay? No. Okay, so then just to be fancy, okay, so what's the first instruction do? Fmul, and I'm going to do V16.2D, okay, so V16 times V5, right? So that's going to get me my x to the first with the coefficient and my x to the third with its coefficient, and they're in a vector register. In this case, I did V9. Okay, now in the previous example, when we were doing the silly linear algebra, I did all the multiplications and then I did a bunch of additions. Well, what could I do to speed this up? Can I do fused multiply adds? Yeah, okay, so that's how I constructed this one is I used FMLA, fused multiply add, okay, for floating point, and did basically multiplications and additions simultaneously, okay? And then on the right there, I sort of show you how I built this up, right? So I've got after that first multiplication, I'm going to get the x to the 5th and the x to the 7th terms, and they're added in to my sort of running total. And then I just keep going with the x to the 9th and 11th, and then 13th and 15th, and I've got those in pairs. Well, then I just need to add up those 2 pairs, and that f add p at the bottom does it. Okay, and then this returns my answer. Okay, so let me open up one other thing there to show you guys. And this is on Canvas, right? So have at looking at it. The other thing I wanted to show you, though, was the SIMD assignment. So this assignment was in, oops, that was not the button I wanted to pick. This one, that one. Okay, there we go. All right, so here's what the polynomial looks like, okay? And the worst our error will ever be is 10 to the minus 12, okay? So then I had to recompute all my coefficients. Mathematically, they're this, but then I had to encode all of them. And okay, so here's sort of the inspiration for this. If you look in the source code for the Apollo guidance computer, okay, so we're talking like early 60s, early 1960s code, you find this little chunk of code. Okay, this is a fifth degree polynomial, but you look at it and you say, okay, those numbers don't look anything like the Taylor numbers that I would be expecting. And they're not. They're from a different approximation scheme called a Chebychev polynomial. Okay, and it works pretty well, okay? That polynomial was published in this book, Approximations for Digital Computers from 1955, and I went and dug up a copy of it. And then I computed it using what I knew about how Chebychev polynomials work, and I got the one slightly under it. I'm not entirely sure why I'm a little bit off from theirs, but I am. And my approximation is a bit more accurate between negative 0.6 and 0.6, but a little bit slightly less accurate outside of that range. So, okay, whatever. So basically what you guys are going to do is you're going to program 3 versions of sine. One version I basically already gave you, right? Because I gave you those coefficients. The other versions are the classical sine from the Apollo computer era, okay, which only goes out to 5th degree and has some kind of funky looking coefficients, okay? But then could I sort of mix the two ideas and say, okay, modern computers, can I go out to a 15th degree? I could. But if I wanted to do it sort of Apollo style, I'd have to recompute a whole bunch of coefficients. So guess what I did? I recomputed all those coefficients. That was another 2 hours of life. Okay, because, yeah. Okay. And so you've got, you can, if there's a link there that's built in that you can click. So here's the Apollo coefficients, the Chebychev coefficients, both as singles and as doubles, and their numerical value, and the Taylor coefficients, their values, their encodings as singles, and their encoding as doubles. And if you click here, you don't even have to type them all out, because I put them all in a very nice pre-typed out assembly ready form just for you guys. Yeah. Look at that. All you got to do is literally copy and paste this. And I've got the 32-bit versions and the 64-bit versions all there for you. Yeah. Okay, so does that make sense? You're writing 3 versions basically. Sine of pi over 2x, which I actually already did for you. Okay, the Chebychev version and the Apollo version. And what I want you to do is basically have the user input using scanf what degrees that they want. Okay, so if I wanted to do 90 degrees, I would take the user's input and divide it by 90 and then pipe it through these functions, because what is sine of 90 degrees? 1, right? Well, what do I have to plug in here to get sine of pi halves? X equals 1. So 90 degrees will get scaled into the number 1, negative 90 would get scaled into the number negative 1. And so the user will input a number between, say, negative 90 and 90, and then you will divide that by 90 and pass it to these three functions. Okay? And that's how it worked on the original Apollo, is that it divided by 90 and then did the approximation. All right, be gone.